What we have here today is a very interestingly named paper. The GAN is dead. Long live the GAN, a modern baseline GAN, authored by researchers from Brown University and Cornell University. Personally, I'm quite surprised to see a GAN paper when the field is dominated by diffusion nowadays. This paper challenges the notion that GANs are difficult to train and offers a new streamlined framework, GAN, that outperforms or rivals state-of-the-art generative models, including popular diffusion models. Let's see what they say. GANs are known for unstable training and often suffer from mode collapse. A successful training often relies on some empirical tricks. To understand the author's main contribution, let's look at the standard GAN objective function, where G and D are the generator and the discriminator. PD and PZ are the real data distribution and the latent distribution. This classic objective can create a single decision boundary. Once the generator figures out how to nudge samples over that boundary, we get mode collapse. GAN gets the name from combination of three losses. In relativistic pairing GAN, each fake image is explicitly compared to a real image. Rather than asking, is this sample real or fake on an absolute scale, it asks, is this sample more real than a corresponding real sample? This strategy forces the discriminator to evaluate local differences around each real data point, eliminating the single boundary degeneracy and reducing mode collapse. In theory, this fixes mode collapse, but in practice, it can still blow up or oscillate if we don't apply proper regularization. To that end, the authors propose applying two gradient penalties, one on real samples and one on generated samples. Both zero-centered penalties encourage the discriminator's gradient to be zero at the true equilibrium. Essentially, this keeps the generator from getting pushed away by overly aggressive discriminators. Now we have a well-behaved loss to stabilize the training. Do we still need old design tricks? The short answer is no. As we can see in the table, starting with StyleGAN2 as a baseline, they systematically strip away tricks as listed in red in configuration B. They also move away from the older 2015 era DC-GAN or VGG-like blocks, migrating to a ResNet or ConvNet style architecture with bottleneck blocks, fixed-up initialization, group or depth-wise convolutions, and inverted bottlenecks. Now, how does it perform? In stacked MNIST, unlike older GANs that might capture only half or fewer modes, GAN recovers all 1000 modes and achieves extremely low KL divergence. In FHQ, GAN hits an FID of 2.75, beating StyleGAN2 as well as several diffusion models under comparable settings. Same story in Cephar 10 and ImageNet. It outperforms or matches large multi-step diffusion baselines with a fraction of the sampling cost. Critically, they also evaluate recall, a measure of how many modes are covered in the distribution. While many GANs fall behind diffusion methods on recall, GAN's recall is on par with or only slightly lower than top diffusion models, indicating strong sample diversity. This work shows that stable training allows for architectural simplification. A well-behaved loss function and modern architecture is crucial for building robust GANs. GAN provides a simple, limited, but strong baseline for future research. One obvious extension is to explore transformers and attention mechanisms to further improve model scalability and performance. That's it for today. Until next paper. See you.